actually get from it. What is the reason why you want to have this dose-response relationship, and what are the information like parameters that we can actually benefit from the dose-response relationship. So yeah, I think most of the introduction will be in the recording. Yeah, so hopefully the students can benefit from it.
Yeah. All right. Yeah. All right. Thank you very much, Dr. Wena, for kind introductions for everyone. Without any further ado, let me follow this lecture 2 about dose-response relationship. Please kindly join.
Sorry, Dr. Fitri. I can't hear any audio, you know. I don't know whether the other students, they hear anything or not. I think you are muted also. Some doubts, right? So I will try my best to answer you. So this is a recorded lecture, but then during the question answer, I will answer the questions live. Okay? So today's lecture will be on the dose-response relationship. Okay, so last week we covered some introduction. So we talked about something concerning what is exactly is the reason why we want to study environmental toxicity, why you want to study chemicals, look into its effect on the human health, and then we also look into studying the risk assessment, whereby we talk about what are the steps to conduct this risk assessment. Okay, for example, you can carry out the risk assessment for like copper in your leg. You can carry out risk assessment of phenol in your maybe river water, or maybe you can carry out mercury in the sea water, and you can carry out any single risk assessment, provided that you follow 4 very basic steps. First one is you look into the hazard identification, whereby you identify what kind of hazard that's available, right? Whether that particular pollutant is a hazard. For example, if you talk about phenol, you look into the data, right? Data whether this phenol, is it hazardous or is it not hazardous? You have to have proper data, which can be obtained from epidemiological study. You can get this data from maybe scientific reference or any other studies that are relevant, okay, and proven, okay, by science. Okay, then after that, once you know that it is hazard, you can carry out toxicology study. Okay, you identify the toxic effect, okay, through toxicology assessment, okay, toxic assessment of the pollutant, and then you also look into the exposure assessment, okay, so that you identify, okay, how toxic is this particular pollutant, and are we exposed to it, okay, and then after that you talk about risk characterization, okay, whereby you take all those data and then you analyze properly, and then you conduct a proper assessment and give justification whether the pollutant in the environment is really going to affect our life. So today we are in week 2. So week 2 we talk about dose-response relationship. So in this lecture we are going to look into what exactly is dose-response relationship and what we can do to evaluate the dose-response relationship of a particular chemicals. And then there are also several parameters from this dose-response relationship know. Okay, so for example, like NOEL, no observed adverse effect level. You also need to know about the LOEL, lowest observed adverse effect level. What are they? And then we also look into what are we going to, how are we going to interpret the different kind of dose response curve. Okay, so what are the things that we can get? Okay, what are the information that we can get from the dose response relationship? So So the outline of our presentation today will cover the understanding and the quantitative relationship between the exposure of a toxicant and the induced effect. So if you have a toxicant, for example, let's say if you have chromium, right? You have chromium and you're exposed to chromium. So we want to understand what is the relationship of the effects of this chromium to our body and the amount of this chromium that we have been exposed to. For example, if we are exposed to 1 milligram, what kind of effect it will affect our body? If we are exposed to 2 milligram, what kind of effect it will be on our body? And we are exposed to 100 milligram, okay, what kind of things that will can be affecting our body, right? Maybe we have rashes, maybe we have certain toxic effect to our liver, maybe we have liver damage, all these kind of induced effects, okay? So we want to understand what kind of relationship between this toxicant exposure or the amount, okay, and the induced effect. And then we also want to understand what is this dose response relationship, okay? And we must be able to describe what exactly is this dose response relationship. And then we also want to look into the effect, okay, effective lethal toxic dose, okay, what are they, if we want to understand it. We also want to know what is the no observed effect level, lowest observed effect level. Okay, these are experimental data, right, which we'll look into later. And then we want to look into what is this margin of safety and the relationship of effective versus toxic dose. So what's the difference between effective and toxic dose? Why sometimes we use the term effective dose, sometimes we use as toxic dose. So generally, these terms effective dose, usually we use it in the clinical studies, whereby we are studying drugs, pharmaceutical drugs, look into how these drugs can help our body to heal faster. Okay, but then of course, this kind of drugs, sometimes the drugs that you have, it can also induce certain toxic effect when its concentration is higher. Okay, when we are taking those doses into our body at higher dose, then it becomes toxic dose. Like for example, paracetamol. Okay, look at the paracetamol. Okay, when you purchase paracetamol, there's a list. Okay, behind you look at the back of this paracetamol tablets, right? There's a list of things that you have to be cautioned. For example, it says do not take more than 8 tablets per day. So why it's 8 tablets? It's because of this kind of study, okay? Effective dose and the toxic dose, which we will look into it in more details in a while. Okay. So when you talk about dose response, okay, first we need to understand what exactly is this dose response relationship, right? So this dose response relationship means that it is a quantitative relationship, okay, which means that this kind of relationship can be quantified. Okay, we know the exact amount. Okay, the quantitative relationship between the dose. Okay, dose means that how much it is, the amount we know, with the occurrence of toxic effect. Okay, toxic end effect, which means we know how much amount of dose can cause how many population to have this kind of toxic effect. So usually we look at dose response relationship, it is a plot of percentage versus the concentration, right? We have two different axes, right? One is the population percentage, which indicates that how many of the population suffers from the ill effect or the toxic effect versus dose itself. Okay, we can quantify the amount of dose that we have and the cost how many people suffering from the effect. Okay, so this kind of dose response relationship, they are based on the observed data. Okay, the observed data means that they are experimental data from animal study. They can be from human clinical study, but it is very rare. Okay, unless it is for something that is good. Okay, beneficial effects. For example, if you develop a new so-called uh, hyperpressure medicine, you can target those people with hyperpressure and look at their response. Okay, we want to see how many people actually be cured from this kind of medicine. So this is okay. This is we can get this kind of data from the human clinical trial. But if we were talk about the toxic effects of certain chemicals, for example, if we want to expose a person to uh, something that is really active to see at what amount it will cause cancer. Of course, no one will want to be involved in this kind of study. So for this kind of study, for the toxic kind of study, we usually the experimental animals is used. Okay. So usually the response that we talk about follows the so-called normal distribution. Okay, we usually in the population we have a lot of different kind of people. Some people they are very sensitive to certain chemicals. Some people they are less sensitive. So we have to look into this kind of normal distribution. So when we talk about dose-response relationship, we want to know what exactly is dose and what exactly we meant about the response, right? So when we talk about dose, we are actually talking about the substance administered at one time. For example, if you have an experiment, right? You want to, let's say, for example, you want to investigate the contraction of a muscle due to a certain chemical, right? So you go to the lab, you get some animals, and then after that you take the animal and you carry out certain experiment to extract the muscle, and then after that you put it in a machine, and then you look into the contraction of that muscle when it is being introduced with a certain drugs, right? So so at a specific time you introduce maybe like a 1 milligram. That is your dose. Okay, the substance that you administer at one time. Okay, and then after that you add another dose. Okay, another dose to the muscle tissue, and then after that you this another extract contraction happens, and then that's the another dose that introduced at that particular time. Okay, so dosage usually we use per unit weight. For example, in terms of milligram, in terms of gram, but the common one would be the milligram because the milligram is the amount usually easier to use, is the amount of specific chemical dose because it is small. Okay, usually the dose that we use is very small. We don't use up to gram because if it's gram, then you will have to use 0.00 something something something, right? So usually the milligram is the most frequently encountered one of our dose. Okay, so exposure on the other hand, we talk about the exposure to a certain dose, right? We talk about how many doses that has been exposed to. Okay, maybe like for example the contraction of the tissue. We tried 1 milligram, and then we tried 2 milligram, and then we tried 3 milligram. Okay, we introduced three doses, but then we expose it to three doses, right? So each of these doses is like maybe 1, 3, 5, but then the exposure is 3 times the number of doses, right? And then the frequency of dosing, maybe we dose it like very frequently, okay, like every hour we introduce this dose 3 times, right? This is one of the way to characterize exposure. Okay. Now the other one is the total period of time for the exposure, right? What is a period of time? Maybe 3 hours one time, for 3 hours, something like that. Okay. So there's a difference between dose and exposure. Dose is the amount of substance administered at one time. Exposure is how many times you expose the dose to the target subject of interest. Okay. So exposure to a certain poison can actually be considered as intentional or unintentional. Intentional means that a person maybe is subjected to a study, right? This person is subjected to the study to look into the exposure of certain maybe drugs to a human, right? And then he probably will be paid for doing such exposure, right? So the other one is unintentional, which means that we are exposed to it without knowing, right? For example, maybe we purchase something to eat, right? Maybe a chocolate bar or maybe a can of fruit, right? And then inside the fruit they put in certain chemicals like benzoic acid, which is very common, right? But then this time it is at a higher level. Okay, maybe unintentionally the supplier or maybe the manufacturer introduced 10 times more benzoic acid in that particular can than it used to be. So this is considered as unintentional exposure. So when this kind of exposure is something that unavoidable, right? So yeah, there are two types of exposure, intentional and unintentional, and the effect of exposure varies depending on the so-called the dose, right? So if the exposure 2 times low dose means that still okay, but then 2 times or maybe single time very high dose, then that would be a problem. So the effect of exposure to a poison will vary, okay, depending on the dose itself. Okay, what is the amount that person has been exposed to, right? So it can be intentional, unintentional, and as I mentioned earlier, it is usually measured in milligram. Okay, it is typical of most exposure in toxicology, right? Although the gram is the standard unit, and many people use gram, right? But then milligram is the most common unit, right? And dosage, sometimes we use something like this: a milligram per kilogram per day, right? Milligram means dose, how much a person has been exposed to, right? When that person is exposed uh, to certain chemicals, he is probably exposed to a lot or maybe a low dose. So this dosage in milligram covers that part. Then kilogram means the body weight. Okay, the body weight of that particular organism. Maybe we are talking about human. Maybe we are talking about something else like animals, right? Like rats. And then days. How many days this person has been exposed to? One example is, let's say we are eating something containing MSG. Right? MSG is monosodium glutamate. It's one of the very commonly used salt in our food to make it into something that is nicer, or what we call as a flavor enhancer, right? So let's say we eat MSG every day. We're exposed to 10 milligram of MSG. Let's say we are, for me, it's about 75 kilogram. 10 milligram per 75 kilogram per day. Okay, so this is the dosage that I have been exposed to, covering the so-called exposure, right? And another one way of quantifying dose is environmental exposure, right? Environmental exposure means that we're actually quantifying relation to the media itself. Like for example, if we talk about water, right? I'm sure many of us chemists hear a lot of this kind of units, right? Milligram per liter, or we call it as ppm, right? Some people call it ppm, right? So this is when we are quantifying with respect to media, milligram per liter in water. Sometimes if you look at the food, right, milligram per kilogram. Okay, and this is very common for food, right? For example, pesticide, right? Pesticides, we want to know how many pesticides in fruit, right? Like apple, we can say that it's 1 milligram per 10 kilogram in food, right? So another one is a milligram per cubic meter, right? This one is in air. So there are many variation of units like ppm, ppb. Right? ppm is actually milligram per liter, but we seldom use that for water because ppm can be misleading. Sometimes ppm is used for air. Okay, this is what I was talking just now in terms of fractioning a dose, which means that we are exposed to the dose at a smaller dose at many different time, right? For example, you are subjected to, for example, here 30 milligram of strychnine, right? Swallowed at once could be fatal, which means we can die when we swallow this large dosage, but we can actually fraction it. Okay, fractioning it into 10 days. Okay, every day 3 milligram for 10 days. The total amount is also 30 milligram. But then if you swallow it 3 milligram for 10 days, it is not fatal. You will still survive, right? So this is what we call as fractioning a dose, right? Total dose, it is harmful when it's received at all at once, but it is non-toxic when administered over a period of time. So this is also part of exposure, right? So exposure to chemicals can be fatal if it's done in a large dose, as I mentioned just now earlier, right? But then, of course, if we split it into many days, then its harmful effect is less noticeable. It is less uh, it is not so fatal, right? Okay, so this slides is just to show you, right? Different substances have different non-toxic level, different toxic dose, and different lethal dose. Okay, depending on what substance you have. Right, for example, alcohol. If you look at alcohol, 0.05% volume over volume will cause nothing, right? It has non-toxic effect, right? But then, of course, if you exceed 0.1%, right? If you drink something containing alcohol that is 0.1%, you will cause toxic effect. But then if you go beyond this, okay, you go to 0.5% volume over volume, you will die, okay, because you have exceeded the lethal dose, right? So carbon monoxide, lethal dose 60%. Then we have different things like aspirin, aspirin 2 tablet, non-benefit non-toxic, which means beneficial. Right? If you take this aspirin, you will have some beneficial dose effect, which means that you can cure fever. Right? When you have fever, you take aspirin, then you'll feel a lot better. But then if you exceed 30 tablets, which is 9.75 gram, then you will start to have certain toxic dose effect. Right? You will have toxic effect in your body. You will have maybe maybe like rashes, maybe like harming your liver and so on. Then you will take 34 gram, which means 105 tablet. It will cause death. Right? So same thing for paracetamol. Paracetamol is very common, especially in Malaysia. We have a lot of paracetamol, right? We don't have a lot of aspirin, but we have a lot of paracetamol, and the beneficial dose is less than 8 tablets per day. Okay, and if you take more than 8 tablets, you will start to have the toxic dose, and then you will, if you take more than that, you will have little dose issue, right? Which means you'll die, right? And ibuprofen, another one is this is antibiotics, 400 milligram, 2 tablets is okay, but if you go up to 60 tablets, 12 gram, then you will die. Okay, so depending on the tablets, it will have, depending on the quantity, you will have different effects, right? So of course you will start to ask, okay, how can we know, right, which amount will cause toxic dose effect, right? Toxic effect or lethal effect, right? So all this data we get it from the dose response relationship, right? So we study. Then there must be someone who study this kind of things. They use the dose response relationship to determine at which dose it will cause the non-toxic effect. Okay, we'll look into it later, especially on this in pharmaceuticals, right? When in drugs, how we can actually look into at which dosage, okay, at which amount it is the beneficial dose, okay. Okay, so after we talk about the dose, the next we want to talk about the responses, right? In the dose response relationship, we have two things. One is the dose, right, in the x-axis. The other one is the responses in the y-axis. So the responses means that it is the change from normal states. We can say that, for example, if you are using maybe some cancer-causing substance, you can say that cancer causing as one of the responses, or maybe the growth of tumor as one of the responses, right? So if you talk about maybe curing, maybe managing hypertension, right, or hyperpressure, right? So we can use like a decrease in the hyperpressure as one of the responses, right? So if we talk about the toxic effect, of course we are using the toxic effect as the responses. If we talk about drugs, then we use drugs as the recovery or maybe the banishment effects as the responses, right? So it can be molecular, cellular, organ, or organism level, which means organism level usually means a death. Organ maybe like organ damage, or maybe for example, if you talk about mercury, we are talking about the central nervous system damage. When we talk about cellular, which means the cell, right? Cell can have a certain effect, okay, like death, okay. On molecular level, at the molecular level, DNA level, okay, maybe DNA damage. Then we have local versus systemic, right? Local area versus or maybe systemic area, right? Or maybe somewhere else. It means like, for example, the drugs has been introduced to your body, then these drugs will travel to the target organ. This is what we call as systemic. And local, it means that it is at a particular exposure area, right? Then we have the immediate, okay, immediately or the delayed, okay. We have the acute, we have the chronic or subchronic, we have reversible versus non-reversible effect, or we have graded versus quantal. So graded versus quantal usually means that usually is like a typical dose response curve, right? You have a dose response curve, right? This will be the response. This is the dose, right? You have something like if you plot like increasing concentration, you have something like this. But if you plot log, right, you will have a sigmoid curve, right? Sigmoid curve means something like this, right? Okay, this is for log, right? This is for normal one, without the log one, okay? No log, right? So this is typical of a graded But if we talk about quantal, usually we talk about two different effects. One, something like that, whereby this one will be the beneficial effect. This one we talk about the lethal effect, right? Or maybe the detrimental effect, not the toxic effect, right? So usually quantal one, you can see it in the drug or pharmaceutical, right? Whereby they have new drugs and then they will go for they will create a quantal kind of uh, dose response relationship whereby they can see what is the dose whereby beneficial effect is observed and then the lethal effects is observed. So this is one curve here is for beneficial effect, the other one is for toxic effect, and then there's this length here, okay, this distance here we call it as the therapeutic window, okay. The larger the window, the less toxic the drug is, okay. This one we will look into it in more detail in a while. Okay, so some example of the toxic responses are, for example, inflammation. When we talk about inflammation, it can be local or systemic response. Then we can have necrosis, which means cell or tissue death. Then we have enzyme inhibition, which means that certain enzyme in the body is inhibited by maybe a chemical or interruptions of the biochemical pathways. And it can be due to competitive or non-competitive. For example, as I mentioned earlier, the example of methanol and ethanol, right? So you have methanol, you have ethanol as two of the chemicals that will be metabolized by the same enzyme, right? So they can have competitive pathway, right, to form certain chemicals like formaldehyde, right, or formic acid, right? So when you have this competitive and non-competitive reaction, they can actually cause certain effects to your enzyme, right? It can inhibit your enzyme, okay, from doing beneficial effects, or it can actually deactivate your enzyme, or you can probably change the characteristics of an enzyme at the molecular level, so that it can uh, bind to other substrates. So there are many different kind of chemical reactions that happens in our body. So enzyme inhibition is one of the responses or toxic effect that we usually look into. And then we have biochemical uncoupling, for example, interference of ATP synthesis. ATP is one of the energy molecule, right? A molecule that provides energy for our body. So if we have this kind of biochemical uncoupling of this chemical synthesis of ATP, then you will feel like lack of energy in the body, which can interrupt certain processes. Okay. Other effects include, like, for example, receptor interaction, which means that it interacts with the normal biological function of a certain receptors. For example, if you look at your cell membrane, it has a lot of different kind of receptors that allows the molecule to go into your cell, right? So if this kind of receptors, they are inhibited, right? So your normal function of this cell membrane will not be uh, able to work effectively. So which means that it may not allow certain chemicals to go in, it may allow certain harmful chemicals to go in, or it may interrupt certain processes that makes your cell not able to perform its normal function. And we also have immune-mediated hypersensitive reaction, which means allergic reaction, uh, immune suppression, which means that increase the susceptibility of a certain organism to infectious agents like virus or bacteria. Then we have neoplasia, which means aberrant cell division and tissue growth, uncontrolled self-growth. You have also tumor growth like neoplasm, tumorigenesis, oncogenesis, which means cancer growth. And then we have malignant neoplasm, which means carcinogenesis, carcinogenic properties, which cause cancer growth in your body. So all these are kind of responses or the toxic effect that can be used as a response in the dose-response relationship. Then you have the genotoxic interaction, which means chemical interaction with DNA, possibly leading to heritable change, which means that it could affect certain DNA, which can be passed down to your offspring. Okay, we have a clustergenic effect or chromosomal effect, mutagenic effect, developmental and reproductive toxicity. So these are also the responses that can be used to monitor for the dose-response relationship. Then we have a type of toxic responses like idiosyncratic, and this is just some example. Okay, it's genetically determined sensitivity or resistance to toxicity. And then we have the primaquine, which is anti-oxidative anti-malarial drug. And then we have nitrite, lack of NADH metaboglobin reductase. Okay, this is one of the enzyme, right? Then another one is the allergic. Okay, allergic is usually caused by the immunological mediated responses, right? It can be triggered by certain things like pollen, pesticides, sulfur, penicillin, and so on. Now we know that this one is a typical dose response, which means more dose most effective, less dose tolerance, right? And then usually it's triggered by contact, right? Contact dermatitis, okay, or anaphylaxis, okay. Okay, so we have gone through what is dose and what is response, right? So dose definition, we've gone through it. Yeah, it's the amount of the toxicant being exposed to a person, and then response, you can see a lot of different kind of response that we can use for our dose response relationship. So we don't have to just stick with only one response. For example, lethal dose, like people use lethal dose because they use death as the response. We don't have to just use death, right? We can use different kind of response. For example, the example that I showed you last week would be the use of mercury, right, as a toxicant, and then you have the effects to central nervous system as the response, right? The effects on how we can actually study it using different kind of responses. Right? We have the list of examples. If you look back at the last week's notes, you look at this mercury. You have a lot of different ways to look into how the central nervous system can be affected. For example, you have the finger tapping methods, you have the Boston naming method, and so on. So many different kind of methods. Okay, so we don't have to just use one response, right? So why you want to do all these things? Why you want to have the dose-response relationship? What's the purpose of having dose-response relationship? It is simple, which is to establish. Okay, we want to establish, right? The fact and causality, which means the relationship of the chemical and its induced effect, okay, or the observed effect. Okay, we want to look into the relationship, as I mentioned just now, the quantitative relationship between the dose and the toxic effect. Okay? We want to establish, okay, the lowest dose whereby the toxic effect can be observed. This is what we call as a threshold. Okay, we want to look at the lowest dose, okay, whereby the toxic effect starts to happen. Okay, if it's death, then we want to look at which of the lowest dose it will cause certain effect to the population, right? Even if it's 1%, we want to see, right? We want to see the lowest dose, and then this is called again is threshold, right? We also want to see the rate. Okay, we want to determine the rate of which the toxic effect occurs in response to increasing dose. What we want to know is that how toxic is a particular substance. Okay, the rate of increase is very important. The slope is very important. Okay, so when you want to look into the effect of a particular chemicals, okay, maybe we want to introduce a certain chemicals to a population. Right, population means that maybe you want to look into introducing a chemicals to a town, or maybe you want to introduce the chemicals to the country, or maybe to a city, right? So we want to look into how this population is susceptible, which means that how they will react to that chemical, right? So if the chemical is introduced, usually the population will respond in such a graph. Okay, this is a normal distribution graph. Okay, so if you look at this normal distribution graph, which means that majority of the population will be undergoing this average effect. Okay, they will be when they are exposed to this kind of chemicals, they will have average effect of that particular chemicals. So if the chemicals is drug, for example, hypertension drugs, right? So majority of individuals who suffers from hypertension will have average effect, which means they are going to have the beneficial effect of that drug. Some individuals will have resistance, which means that the drugs that they take will not be effective, right? So if it's not effective, then they will not feel the beneficial effect. Some, of course, another portion will be sensitive individual, which means that they'll feel all the effects, the maximal effects of that particular drug. Okay, so if it's a pollutant, right? Let's say we introduce a pollutant to the city or population. The same thing applies. Okay, some individual will have average effect. Okay, when they are exposed to that pollutant, they will have maybe certain toxic effect to their body, maybe rashes, right? Some will have sensitive effect, which is hypersensitive. They will start to suffer a lot. Okay, they will suffer a lot from this just a small amount of chemicals. We are talking about the same dose here. Okay, the same dose, but then it triggers sensitive effect to this part of the individual. On the other hand, we also have the minimal effect individual, which means that at the same dose that cause uh, people to be very, very sensitive, right? This group, okay, the hyposensitive group, is very resistant to the chemical. They are not feeling anything. So we always have this kind of three classes of different people. Okay? It always follows normal distribution. Okay? Any effects follow normal distribution is because we all have different kind of body. We have different biochemical system. We have different tolerance to a certain chemicals. That's the reason why we have a variation. Okay, so this variation is very important in our survival, right? But then it also causes a lot of problems, right? Especially to sensitive people towards toxic chemicals. So when we want to design a policy, right? When we want to design something, because although we have sometimes we have to consider sensitive individual, it also depends, right? Depends on many factors, for example, economic factors or practicality. Okay, so this is something that has to be carefully implemented to ensure that the population is safe. Okay, so if you look at the recent example, okay, one recent example is the introduction of this COVID vaccine. Right, COVID vaccine, of course, you heard a lot of people complaining, right? That when they take this certain COVID vaccine, they have certain effects to their body, like rashes and so on, right? So these are generally the sensitive individual. Okay, they represent the minority, but of course we hear a lot of this because uh, we can say they make a lot of noise. Okay, they talk about what are the effects they have. Then of course the new sensationalize this thing. They make everything looks very crucial and right something like that, right? So what I'm trying to highlight here is that of course when you want to design a policy, okay, for a country, we have to make sure that the country gets the effects, okay? Because sometimes it's very difficult to say that this particular drug, okay, this particular vaccine has no effect, okay? But we can only say that it has no effect to majority of the individual, okay? So these are the normal distribution parameters whereby the mean plus one standard deviation is about 68.3% of the population. Then we have the mean plus two standard deviation, 95.5% population, and so on. Okay, so all this just to tell you that which population are in the average zone. So if you look at the normal distribution, right, you can see that this is the like normal distribution. Majority will be like more than 90% will be under the average zone. Okay. So we know that certain population they are susceptible to small amount of toxicant, while certain population they are resistant to a large amount of toxicant. Right. So we need to design a dose response curve that takes into account the average population. Right. So usually the dose response relationship only accounts for the average population. Right. And if you look at this, right, this is the typical dose response graph. Right, this is whereby you have three different regions. Region one, which is no effect range, which means there's no effect, right? Then we have the range of increasing effect with increasing dose, right here. You can see it's very fast increase, and then we have the maximum effect range, okay? And then the increasing effect, this is the response, okay? This is usually in percentage, right? Percentage of the population. right? And then you have the dose, increasing dose. So in this increasing dose, most of the time we will use log, okay, the log scale. Okay, so log scale, when you plot it, you will see something like this, right? You will have a sigmoid curve, okay, and this is a typical graph of the dose response curve, okay. So there are important assumptions of the dose response relationship. Number one is that there's always a dose whereby no response occur, okay. This is a part, right, of the area whereby there's no response occur. Okay. On the other hand, you have another part, another assumption, okay, which is once the maximum dose is reached, that means there's no further increase of dose will result in any increase in the effect. Okay, this is logical because at this point usually it's already 100%, which means 100% of the population is suffering from the effect. Okay, so this is a typical dose response curve with the assumptions. So this is for all the chemicals except for the carcinogenic chemicals. We treat carcinogenic chemicals differently, right? Because we have the assumption that carcinogenic chemicals will start to have response when it's exposed at small dose around here, right? There's no first assumption is not valid. There's no dose that has no response. Okay. So this is, like I mentioned, the typical dose response curve, the same as just now, but this is more detailed. Okay, you can see this, all these points, they are experimental point. Okay, they have to be experimental point. Okay, and then this is a standard deviation. You can see this one, right? The error bar, right? Okay, so each of these you have a lot of different points. Okay, which is the error bars for the data, and then you have the point. Again, there's one point whereby you don't observe any effect. This is what we call as a threshold. Okay, this is a threshold, right? And then yeah, data from exposure of test organism to doses of toxic substance. So this is the response, okay, and this is the dose in log scale. Okay, usually it's in log scale. Okay, response is percentage. This is in percentage. Okay, this is in terms of the percentage of individual with the symptom or the response. If it's deaf, then it's the response is deaf. Okay, if it's a problem to the central nervous system, then the response is issues to the or problems to the central nervous system. Okay, so this is a typical shape, as I mentioned, for non-carcinogenic toxicant, which means that this is any chemicals that is not carcinogenic. We can use this curve to describe the dose response curve. Okay, so you have 100 here, which means 100% suffers. Okay, this is the areas whereby the maximum effect has been hit. Okay, so at this dose, if anyone exposed to the chemicals, 100% you will die. That's the meaning of this. Okay. So from the dose response curve itself, we can actually measure something called a medium lethal dose. Okay, if we use death as the criteria, we can actually use the medium lethal dose, LD50, right? And we look at the typical graph, right? It's something like this, right? And then you have 100% here, right? Then you have 0%. Then there's a point whereby it's 50%, right? So there's a dosage here. If you look at this dose response graph, if you plot a line, right, you look at this dose over here, right? This is the LD50. Okay, this is a lethal dose. If the criteria, the response is death, this is a lethal dose that can cause 50% of the organism to die. And this is one of the most widely used parameters to compare the toxicity of chemicals, right? As I mentioned, I think last week I mentioned about LD50. Okay, this is quite widely used. In fact, I also use this LD50 in several of my publications. We use LD50 to quantify the toxicity. Okay, we compare the toxicity, right? LD50 for certain organism, microorganism. We use Vibrio fischeri, which is a common microorganism, and we use it to measure the toxicity of treated wastewater. Okay, so we can actually measure, what I'm trying to say is that we can actually measure and compare the toxicity using the LD50 parameter. Okay, so you often use to compare toxicity okay, only measures lethality, right? Where this LD50, because the L here stands for lethal, so we only actually use it to measure lethality, which means death. Then best for quantum data, right? Quantum data means that you have things like drugs, right? You have a effective dose, okay, beneficial effect, and then the other one is the toxic effect, right? This is typical quantum data, right? Best got acute exposure, okay, which means direct, one time, one shot exposure, right? That means acute. Acute means that is direct, okay, which means that you are exposed to a large quantity at one time. Okay? Tells nothing about slope, of course. Slope is very important because slope tell you about the toxicity of that particular chemical, right? But this LD50 does not tell you about slope. Okay, regardless, we can actually use this LD50 or the lethal dose 50 to actually compare between different kind of chemicals, right? For example, ethyl alcohol, you have 10,000 milligram per kilogram, which can cause 50% of the population to die. And then you have ferrous sulfate, 1.5 K, okay, milligram per kilogram, which can cause 50% to die. And then you have nicotine, which means 1, and so on. So if you look at all these values, right, you can see ethyl alcohol very high, whereas nicotine very small, which means that nicotine can actually cause more death to the population. But first, when we talk about this kind of comparison, usually when we look into this LD50, right, we also mention the organism used for this kind of study, right? If it is not mentioned, then usually it's very difficult to ascertain whether this kind of results is it valid or not, right? So another approach that people use to look into more accurate comparison is to look into using milligram per kilogram, for example, this unit, right? So that it can give a more accurate comparison. Um, right? If you use animal, you use other kind of organism, then if it's milligram per kilogram, then we can actually uh, give us some sense of whether uh, how much is needed for human, right? So because there's a relationship between mass, okay, a mass of an organism and the toxic effect. Okay, that's why when you look at the horse, okay, horse, when you want to use, you want to let the horse sleep, or maybe some animal, like lion, they caught a lion, they want to let it sleep. They calculate the mass of the lion, and then they use a tranquilizer. They measure the amount of tranquilizer needed, and then uh, they inject into the lion or the horse, right? So the mass itself is proportional to the amount of uh, chemicals that you need, okay, for the effect to happen. So that's why using milligram per kilogram is gives a more accurate representative. So the shape and slope of the dose response curve is very, very important, right? Because the shape and curve of different toxicant give you a different interpretation and different uh, information, right? For example, you look at this two, toxicant A and toxicant B, right? So these two toxicant, they have different threshold. The threshold is the point, okay? Usually it's experiment data. It has to be experiment data. The point whereby there's no toxic effect observed yet. Okay, so this is what we call as the threshold effect, as what I explained just now. Okay, so the slope itself, right here, you can actually plot the this graph, the sigmoid graph, and you can determine the slope, right? Okay, slope itself can tell you, okay, between these two toxicants, which one will give you more adverse effect at higher concentration, okay, at increasing concentration, which one will give you more effect, okay. So knowledge of the shape and slope of the dose response curve can be actually be used to predict the toxicity of the substance at a specific dose level, right? So you can actually predict, okay. So it's very important because it is giving you different kind of information. So if you look at toxicant A and B, okay, it's a method to compare this and this. You can see that toxicant A actually uh, become more toxic, okay, with increasing dose compared to toxicant B, whereby the toxicity is actually slowly going up, right? Okay, you can see it's slowly going up. So at this point, okay, at higher dose, toxicant B can cause 100% response, but then compared to toxicant A, need a lower dose here. Okay. So similarly, if you look at this dose response relationship, you have toxicant A and toxicant B. So they have different size and shape, right? So toxicant B actually is less steep compared to toxicant A. So if you measure the steepness, right? If you look at the steepness of these two, you can tell very easily that toxicant A is more toxic. Okay, with a small increase of the concentration or dose, you will actually have a lot of effects. Okay, more people will be affected, right? And then it reach 100% very fast compared to the toxicant B, whereby it needs higher dosage to achieve 100% of the response. Okay. There are also many different threshold, or what we call as different parameters that are used to compare between the different toxicant, okay, in terms of their toxicity or their effectiveness. So for example, we have ED90, EC50, LC10, or TDLO. Okay, so the difference between all these is just in terms of the percentage of population being affected, and difference in terms of whether we are looking at the drugs that gives a positive response, or maybe we are looking into the toxicant that gives a different response. So all these are very important information that gives us the value, okay, the dose that can start to give us some effects. For example, ED. Okay, ED means that effective dose. Effective dose usually we see it in pharmaceuticals, whereby people use it to look into the percentage of population that is getting the beneficial effects from a certain drugs. For example, if you look at the dose response relationship, something like this, right? Whereby this is 100%, this is the dose, right? So if you look at ED90, that means it's 90, right? Then you look at this the dose, right? This dose corresponds to 90% of the population getting the beneficial effect from the drug. So ED means effective dose. So effective in terms of getting the beneficial effects from the drugs. And then we have the EC50, which is the effective concentration, which is pharmaceutical in vivo, sometimes in environment toxicology. So this, in terms of the concentration of those, they are actually the same thing but different unit. And then they are used, yeah, sometimes they are used in the different areas. For example, for this case, one is in pharmaceuticals, one is in vivo, blood, environment toxicology, whereby they are looking into the concentration and in terms of the they are looking into the amount in terms of the concentration on compared to the pharmacy, which looks into the concentration in terms of the dose, okay, the amount in terms of the dose. And then we have lethal concentration, LC. Okay. LC means death. If you look at the lethal, the word lethal here means fatal, which means death. So that means using death as a criteria, as a response, right? So LC10 means that they look at the 10. For example, if you look at this graph again, lethal concentration 10%, 10% population, you look at the number here. Again, this is a lethal concentration, right? So on the other hand, this TDLO and TCLO, it means one is the lowest published toxic dose, the other is the lowest published toxic concentration, right? So that means the lowest ever published dose that gives you some effect, okay? Then we have something called the Therapeutic Index, which is called the TI, right? This is basically something that we use to look into the relative safety of a drug, right? So this TI, Therapeutic Index, is actually the ratio between LD50 and ED50, which means this is a lethal dose 50 divided by the effective dose 50. So if you have a very large number, right, this ratio, right, that means the drug is safe. For example, if you look at this, it is 10, right? If the ratio, TI ratio is 10, which means that we can actually consider it as safer compared to when you have TI of 3. Okay, we'll look into why we say that in a while. Okay, so the slope of the dose response is very important. So let's look at a typical example. So this is a typical example of a therapeutic index, or what you call as a TI index. Let's see how we can actually get it from this kind of graph. So in this graph, this is a dose-response relationship for a drug. Okay, this is usually you will see it in clinical studies, or when a pharmaceutical company wants to release a drug into the public or population. They have to have this kind of dose response relationship, whereby looking into the effective dose and the toxic dose, which means that every drug that you have, okay, every drug that introduced into the society or the population, that particular drug will have its effective dose, which means it is giving a beneficial effect to the population. And to some extent, when you have the dose at higher level, you are actually having toxic effect. So this is very common in all the drugs that you will find. Okay, so that's why it is good to have a very clear separation between the effective dose response curve and the toxic dose response curve. Okay, so these two, you have to have a clear separation, which means that you have to have a large gap between this. Usually we have something called a therapeutic window, okay, which measure this distance, right? The larger this distance is, the better it is in terms of the effectiveness, okay, of the drug without causing any negative effect to the population. So why I say that, okay, if you look at this kind of graph, okay, if you look at this two different curve, right, for a particular drug, right? So if you want that particular drug to be 90%, okay, 90% effective to a population, right? If you look at this 90%, right, effective to a population, right, you have it here, and then you will see that the amount that you need is what we call as the ED90, effective dose 90, which means that you need 90% of this population. You have to have this dose, okay, ED90 dose, right, effective dose 90. But you have to bear in mind that if you look at the toxic dose graph, okay, the dose response relationship here, if you have this ED90, you are actually causing toxic effect to about maybe 3% of the population, right? So you have to look at this graph, and then you have to understand that if you actually want to release this drug into the population, 90% will benefit. 90% of population will benefit from this, right? But then there will definitely be 3% of people who suffers from the toxic effect of this drug. Okay, so we have to know that this kind of things actually happens. So we have something called the therapeutic index, which is the LD50 over ED50, which means we can actually measure whether this drug is to some extent safe or not. So LD50 is lethal dose 50, right? LD50, which means 50% of population is like having issues, okay, or die because of the this dose. Right, let's look at this example. If we look into the 50%, right, toxic dose, let's say this is death as a lethal to get the lethal dose, 50% here. This is a 50%, okay. Then we have ED50, effective dose 50. This is an effective dose 50, ED50. Okay, so this value and this value, right, you have these two values. So you take the LD50 divided by ED50, this one divided by ED50, right? Then you will get a number. So you can see the larger the number, okay, the larger the number, which means if the larger the number, that means the value of this LD50 is actually far to the right, right? Right. So the larger the number, the better the separation between the effective dose response curve and the toxic dose response curve, which means that the toxic effect of the drug is less, right? So this kind of knowledge, okay, of the effective and toxic dose levels is very important to aid toxicologists and clinicians to determine the relative safety of the drugs of the pharmaceutical. So we have to bear in mind that not all those response curve will have the same shape. Even though it's from the same drugs, it can have effective dose shape and toxic dose shape very different. So for example, let's look at this one. Okay, this graph correspond to two different shape, right? So this is for the same okay, for the same drug, okay, from the same pharmaceuticals. But then when you look at the effective dose and the toxic dose, then they give a very different kind of shape. Okay, from this shape you can see, right? Let's say you want this drug to be very effective for 50% of the population, right? So effective dose is for the red one, right? 50% of population, you have it here, right? So it's over here. This is the dose that is effective for 50% of the population, right? But then if you want, let's say, to look at the toxic dose, okay, what is the percentage that will cause toxic effect to the population? You look at this one. For 50% population to have the positive effect, you will have, I think here is about 10% of people suffering from negative effect. So if you want to design a drug that is 100%, right? Let's say you want to have a dose that is 100% effective. It's not possible because you're likely going to kill everyone, right? At this effective dose. So which means that the effective dose is also toxic dose. It also causes a toxic effect to that particular organism or person, right? So this is not a very good drug. Okay? Let's say 75%, right? You want 75% of the population to have beneficial effect. You have it here. But then for 70%, you will have 50% population suffering from the toxic effect of that drug. So this is very risky, very risky drug. Unless the toxic effect is not very critical, then still okay lah. You can still use it. Maybe the toxic effect is like migraine or maybe constipation or maybe something that is not so serious, and at least still okay. But then if the toxic effect is like death, then this is not a very good drug, because to cure to 75%, you actually have to have 50% of population being having the lethal effect. Okay. We also have this thing called the NOEL and LOEL, which also I have talked about last week. One is no observed adverse effect level. One is the lowest observed adverse effect level. So these two, they are something that we can use to quantify, okay, and determine which dosage is safe. Okay, so these two, they are the experimental data. So bear in mind, these two are their actual data points, okay, from human clinical or animal study. So they are not predicted. Okay, we cannot use predicted for toxicology study because it can be very risky, right? Because toxicology study involve effects, right, and can cause human, okay, to suffer from lethal, like fatal effect or maybe die, right? So NOEL and LOEL, they are based on experimental data, okay, which means NOEL means that the no observed adverse effect level, the experimental data that has not shown any adverse effect level, whereas LOEL means that the experimental data at the lowest point that gives you the certain effects, the adverse effect. Now let's look at this example. Okay, so this is the example of LOEL and NOEL. Okay, you can see this is the lowest observed adverse effect, whereas this is the NOEL, no observed adverse effect level, right? So you can see this is the lowest level. Although you can see here you start to have the effects, right? This curve is drawn by you. Okay, in actual sense, the experimental data is only here, right? This is experimental data, and right, you can only have this experimental data, and then you plot the graph, right? So we cannot say that the LOEL is here because there's no data to prove it. We only have data at this point, so that's why we say that this is your lowest observed adverse effect level, right? So the no observed adverse effect level, we cannot say it's over here because here can cause certain effect, right? So that's the reason why we use this point, right? So these two, as I mentioned, experimental data. So using the NOEL, no observed adverse effect level, we can actually calculate what is the reference dose. So reference dose means that the lowest acceptable level that you can ingest or be exposed to that particular toxicant or chemical, right? So reference dose is actually calculated using this formula, using the NOEL, which means the no observed adverse effect level, divided by something called the uncertainty factor. Okay, so this uncertainty factor can range between 10 to 1000. It can actually be higher than this 1000 also. Sometimes it can be 2000, 3000. Yeah. So it depends. Okay, this uncertainty factor, right? So generally, this reference dose calculation, you can see that it is far below this no L. Okay, no L is over here, no observed adverse effect level, and the reference dose is quite far. Okay, this is to take into account all those uncertainty factors and issues that will affect a person. So reference dose is generally regarded as a safe dose for the toxicant. So generally, reference dose equals to no L over uncertainty factor, whereby the uncertainty factor actually composed of many things. Okay, so for instance, you have these 5 different parameters that determines the uncertainty factors. Like the first one, FA, which is the extrapolation from animals to human. So if you use animal studies, you actually want to extrapolate it to human. So in that case, you have to add maybe 10 in this uncertainty factor, right? Then, of course, we also look into differences in human susceptibility, right? We have a variation. For example, we have hypersensitive, some we have hyposensitive people, right? So we have to also take into account using this reference dose. Otherwise, if we did not take this into account, those who are hypersensitive will be affected, right? So we also need to look into adjustment factor for subchronic data sources, then adjustment factor for low L, when low L is used, okay, which means lowest adverse effect level, okay, and then adjustment factor when data are incomplete. So all these, they are some of the adjustment factor that you need to take into account when you want to calculate the reference dose. So all these takes can be combined, and they are the uncertainty factors in the calculation. So another one thing that I talk about is comparison of toxic effects. So we have a certain definition for us to look into: potency versus efficacy. So potency means that the range of doses over which chemical produces increasing responses, which means you look at the slope itself. Okay, so at which range this particular chemical or maybe toxicant will produce the highest increasing responses, right? So the other one is efficacy, which talks about maximum response. What is the highest response, the maximum response, which means the limit or the plateau of those response curve. So let's look at the example. Okay, example of this potency and efficacy. So if you look at this those response curve for 4 different chemicals, so you have chemical A, chemical B, chemical C, and chemical D. So if you talk about potency, okay, when we talk about potency, which means that the range whereby there's a high response or increasing response. So the range here, right, for A is here, B is here. So of course A is more than B, right? Whereas for C and D, right, C is here and D is here. So definitely C is more than D. Okay, so A is more than B and C is more than D. Okay, because they are at the left side. Okay, this is at the left side, this is at the left side. This is the range whereby you have the maximum response. Whereas for this, D is here. Right. So the other one is efficacy. Efficacy is looking at the limit of those response. Right. A and B, they achieve almost the same level. Right. So that means they are the same. A equals to B. Whereas C and D, okay, for C you only have until here, 30%. Whereas D you have 90%. So definitely C is less than your D. So this is how we look at the potency and the efficacy of chemicals. Right. So from here we can actually compare between the potency and the efficacy. So potency of a chemical generally is actually related to the dose required to achieve the toxic effect. So if you look at this dose response relationship, we can actually use the potency to compare between different kind of toxicant. For example, the example that we look at in the previous slides, we can actually look into comparing the potency of A and B. Okay, and in extreme case, of course, the toxic response, sometimes we use lethality as our response, right? And it is also related to the animals used to perform toxicity experiment, right? So you look at this table over here, you can see that for dioxin, right, rat and guinea pig gives a very different LD50. Okay, one is 0.0006, one is 0.045, right? So you can see there's quite a different gaps. So it depends on the animal itself. So in other words, if you want to compare, you also need to know what kind of animal was used for the study, and yeah, you can actually compare the potency of the dose response curve. So the potency of poison usually are compared using signal words or categories. For example, if you look at this table, right? Table over here, you have highly toxic, moderately toxic, slightly toxic, or practically non-toxic. All these they are considered as the category. Whereby you have the signal word required on label. For example, danger, poison, warning, and caution. So these are considered as signal word here and the category over here. So they are all based on this LD50. One is LD50 oral and the other one is LD50 dermal. So this data, whether it's danger, poison, all these they are arbitrary. They are signal word based on the preference. Right? So but then all these they are based on the data, the LD50 data. Okay, either the LD50 data from animal studies or maybe from the human studies. They use it and then they classify it based on category and signal words. Okay, and they use it as in to classify the potency of poison. So generally, the classification, as I mentioned, they are arbitrary. Okay, typical scale they usually use something like this: extremely toxic, moderately toxic, with numbers. Okay, these are actually arbitrary, and maybe you have slightly toxic and relative harmless. Okay, depending on the chemicals and animals or human study. Okay. So there's another parameters called so-called margin of safety. So this margin of safety, to some extent, is telling us that whether this particular dose, what is the safety net, which means at which point it is still safe. So it is measured by LD01 divided by ED99, which means that it looks at the lethal dose. For example, let's say for this dose response relationship, you have two different kind of graph, right? This is the one that I showed you just now, quite similar. Effective dose is red color, okay? And then the other one is the toxic dose. Okay, for this case, let's look at it as a lethal dose. Okay, as in the response for the toxic dose is death. Okay, so this one we put it as a lethal dose. Okay, so if we look at LD01, okay, that means 1% here. Okay, you look at the dose here. Let's say this dose is 5, right? 5 ppm. Let's call it 5. And then ED99, effective dose 99, which means here, okay, over here, it's supposed to go to the red color one, okay. Here maybe it's 50. So you are actually looking at LD01, LD01 which is 5 divided by effective dose 99 which is 50, right? And you will have 0.1. So this is how we calculate the margin of safety, right? Based on this kind of calculation, LD1, okay, they mean lethal dose at 1% population, which means that at least those 1% of population will die, divided by effective dose, whereby 99% of the population will have the effective effect from the chemical. So if you use the margin of safety, it is actually accounts more for slope difference, right? You calculate, if you look at the calculation between different kind of dose response, right? You can actually see that it actually accounts for more slope differences. The ratio dose within the lethal range with the dose that is 99% effective, this is what called as the margin of safety, as given by the formula here, LD01 over ED99. Okay, this is the formula. So the physician must be cautioned if it's describing the drug that has a margin of safety at less than 0.1. Less than 1. So the one that we observed just now is 0.1, right? The one that I give you an example, okay, before these slides, is 5 over 50. which is 0.1. So this is something that is not good. Okay, as I mentioned earlier, this kind of graph is not good. So a physician, okay, or doctor must be very, very cautious if you want to prescribe a drug that has a margin of safety of less than 1. Okay, 0.1 is not acceptable. You have to have higher. So if, let's say, if you look at the dose response curve that is very, very far apart, right? One is effective, one is little, and let's say this little one, LD01, right, here is, let's say this is 50, and then this one, your effective dose 99% here is 10. Then this will be different, right?
Yeah.
This will be like LD01, which is 50, divided by effective dose of 10. Then this one you have 5. So this means that the drug itself has a very good margin of safety, which means that it is quite effective and it is acceptable. But if your margin of safety is less than 1, then you have to be very, very careful. Okay. Neither TI, Therapeutic Index, or margin of safety works for chemicals with no beneficial effect. Okay, so it means that we have to have this kind of graph, right? With one beneficial effect and with the toxic effect. So it is for those pharmaceuticals or drugs that has certain effects, good effects to human, and to some extent, sometimes it has toxic effect. Okay. So most of the dose-response relationship, it is actually sigmoid shape. Okay, but of course there are also some dose-response relationship that is not really sigmoid shape, right? Some they have a slightly different shape. The one that is sigmoid shape, sometimes we call it as the monotonic, or what we call as a traditional dose-response relationship. There are also non-traditional one, or what we call as non-monotonic. For example, U-shaped dose response. Or we also have something called a homeostasis, okay, dose response, which accounts for different kind of chemicals. So let's look at certain example of this kind of dose response relationship of non-traditional one. So at least we can know what kind of non-traditional dose response relationship are present, and why they are present. What are the kind of chemicals that are present? So usually the U-shaped one is for essential nutrients, sometimes heavy metals, and sometimes those vitamins. Then you have homeostasis, usually is for hormones, okay, like thyroid hormones. You have so-called estrogen, testosterone, all these kind of hormones. Okay, they are following this homeostasis dose response relationship. So this is how a U-shaped dose response curve looks like. So you have a deficiency, then you have the region of homeostasis, and the other one is the toxicities level. So this is usually for nutrients, like some nutrients, if you have not enough, then you have deficiency. So you start to observe the adverse effect, right? Yeah, at this point. So if you are very low, then if you have the just optimum amount, then you have this region of homeostasis. Either no effect, or sometimes you have beneficial effects to your body. It will not interfere with any of your processes or chemical reaction in your body, then still okay, it is well maintained. But if you have excess of this and you have high dose, then you have the toxicity effects. Okay, so this is how it looks like for the U-shape dose response curve. It also exists. So just to let you know, for nutrients. So the other one is the homeostasis effect, whereby usually we see it in hormone. Sometimes at lower doses, it can cause a good adverse effect. Okay, here, and then after that, when you have increasing doses, it starts to give you certain adverse effects. For example, thyroid hormone, which if you have thyroid hormones at the optimal amount, it will start to have a protective effect. But then as you have higher increasing dose of this thyroid hormone, it starts to have certain adverse effect. It start to trigger a lot of different reactions in your body, and then you will start to have problems. But this is how the homeostatic dose response curve looks like, right? So we also have something called a cancer dose response curve, which usually we assume that it is linear, intercepting at 0, 0. This means that we are making an assumption that says any exposure to this kind of chemical will cause cancer, even though a very small amount, it starts to cause cancer to the population, maybe 1% of the population or 2% of the population, right? So cancer have this kind of assumption, okay, and of course, for cancer, the slope factor is very important because the slope factor determines how carcinogenic a particular carcinogen is. So usually for cancer, we use this so-called linearized multi-stage model, whereby we assume there's no threshold effect. Threshold, as you may recall in the earlier lecture today, we look into the area whereby there's no adverse effect. Okay, there's no effect at that area until the point where it starts to have effect. Let me just draw it out. Okay, so this is the threshold. Okay, whereby there's no observed adverse effect here, right? And then after this threshold, you will start to have increasing effect all over the place, right? More population starts to have effects to their health, right? So for this carcinogen, we actually assume that there's no threshold effect. There's no such thing as this region. So it always starts from zero, okay? And actually we extrapolate it based on this zero from the upper confidence level of the lowest dose that cause cancer in animal study. Okay, so we actually analyze the slope to look into the carcinogenic effect of that particular carcinogen. So this is how it looks like. Okay, for doing this linear plotting, usually when you use this carcinogen, okay, let's say you have percentage risk of cancer here, right, and you get the data, okay, with the dose log scale, then you will get something like that, resembling this kind of curve. Okay, this is one, this is one, this is another one. This is the data that you can get. Okay, you can see that this is the lowest dose that cause cancer, right? There's no other dose already. This is the lowest dose, right? And then you have 1, 2, 3, these three data point, and then you want to plot the straight line, okay, starting from zero. Usually carcinogen, we will use this method, okay. Then after that, you extrapolate this, you draw this until the upper boundary. So you can look at the data point, right? Each of the data point has an error bar, right? So we start from this upper boundary, and then we go straight all the way to zero, right? So this is a straight line that we draw for the carcinogen, right? And then the slope for this carcinogen is actually your so-called the slope factor, which measures and allow us to compare different carcinogen, right? So carcinogen risk assessment is the cancer slope factor, right? And we actually use this upper bound estimate, okay, of the probability, and then draw a straight line, right, and to get the slope. And it is usually expressed as milligram per kilogram per day. So before we end our lecture today, yeah, just want to recall what we have learned today. So we have looked into what exactly is dose, right, and also response. So dose is generally means that the amount of toxicant or any chemicals that is administered at one time, whereas response is the observed effect that is out of the norm, so that we observe, right? So dose response relationship, we also have looked into what exactly it is. What are the different shapes of this dose response relationship? What are the parameters that usually we look into? What is therapeutic index? We also look into what is margin of safety. And before we end our lectures, we also want to look into one final example. So this example is to give you some insights on how this dose response relationship is actually carried out, okay, in the lab. Okay, sometimes we do it in a larger population study, which is more difficult, but sometimes we also can do it in the lab, okay, to look into a very basic dose response study, right? So in this particular example, I just want to show you how we can actually conduct a dose response relationship based on this acetylcholine effect, okay, using frog rectus muscle, right? So we want to see how exactly this frog muscle can respond to this chemical acetylcholine, right? So generally how this is carried out is that you can see the frog over here. The researcher will take this frog, right, and then after that he will get this muscle. Okay, the muscle over here. He will take it out from the frog, and then after that, the students will put into this machine. Okay? This machine is what we call as the organ bath, right? They will put it into the machine, and then after that, they will add certain chemicals. For this case, is acetylcholine, right? They will add these chemicals into this organ tissue, the tissue, okay, the muscle, right? So when they add into the tissue, like you can see over here, right? They add it, and then after that they have this something here, and then after that there's this frontal writing lever, right? So when it's exposed to this chemical, so this tissue will, to some extent, it will contract or it will expand. Okay, it depends on what kind of tissue you're dealing with. For this case, what you will see is that it will give you this kind of signal, right? So when there's a contraction, you will see this kind of signal over here, right? So this signal is proportional to the amount of acetylcholine that you introduce to the muscle. Okay. So we usually call this results of chymograph. Okay, now this is a contraction, right? Contraction of the muscle tissue, and then from what you will see is that you'll see something like this, right? This is the graph that you will see, right? So from this, right, you can see that 0.1 you give this kind of a contraction, 0.2 is slightly higher signal, 0.4 much higher, and then after that you have 0.8, which is very much higher than 0.4, and then after 1.6 is almost equivalent to 0.8. This is what we call as a threshold. We have already achieved the maximum limit. Okay, so if you look at the data, right, the dose given 10 microgram, 20, 40, 80, and 160, and the response. Okay, response in height, we have 0.3, 0.8, 1.4, 1.8, and 1.8. Okay, so actually from this data itself, you can actually plot the dose response relationship. So you can actually try out, okay, how to plot the dose response relationship from this data, okay, that is given. So this data, first thing that you have to do is to convert the response into percentage. Okay, dose response is in percentage. So this is an experiment that you can actually do in the lab. So this is to show you that this kind of study is actually being conducted in experiments, right? In experiments in the lab to really understand what kind of dose response curve is and how it is actually giving us data, right? That we can use to maybe to determine what kind of level that we want to set, what is the margin of safety, what is LD50, and so on. Right. So from here, after you have determined the percentage, the next thing that you have to do is to convert this dose into log, okay, into log dose, right? And then after that, you plot the graph, dose versus the response, okay, response here in percentage, right? Then you will see that if you use the log, right, you will get something like this. On the other hand, if you don't use the log, you will not get the sigmoid curve. You will get exponential curve like this. Okay, so the sigmoid curve is the more typical curve that we see in dose response relationship, right? Well, thank you so much for listening to the lecture, and hope to see you again. If you have any questions, just let me know. Thank you.
All right. Thank you very much, Dr. Wenda, for very comprehensive and insightful lectures. Even we can, how to say, see many great examples, yeah, how to do testing for determining the, how to say, toxic effect on certain animal. And from the lectures, if I'm not mistaken, there are many concepts that been delivered. Firstly, about the quantitative relationship between the toxicant exposure, yeah, and induced effect. And then very detailed, Dr. Wenda explained to us about the dose response relationship. Yeah, he provided us also many great example how to determine any types of those response relationship. And the last part, I can mention that Dr. Winda also provide us the concept about the how to determine the effective dose, lethal dose, toxic dose, non-observed effect dose, how to determine the margin of safety, and also relationship between the effective dose and toxic dose. And in the end of the lectures, he also provide us the good examples of how to determine the carcinogenic effect, especially how to determine experimentally, based on uh, the the dosage response. So I do believe here uh, all students or other participants have any questions or comment due to the lecture. So please feel free to raise your questions. You can open your audio, also video if possible, or you can type your questions in the chat box. Any question, please? Yeah, maybe I can ask you the question first, Dr. Wenda. So,
Yeah, sure.
regarding to the how to say variance in population's susceptibility, usually we also how to say I've been read from certain reference about the concept of hypersensitive and hyposensitive. In your case, you explained to us about the persistent effect and also sensitivity. Is it the similar concept or
Yeah.
different?
The hypersensitive and hypersensitive usually it is they are like more susceptible to this drug effect, right? For example, if you are talking about the drug, right? So usually yeah, we should be concerned about them. But then in terms of making policy, if we talk about making policy to take into account those hypersensitive and hyposensitive, usually it is not so simple because sometimes we have to take into account whether it is economical to consider them inside the policy or not. So there's a trade-off, as in if we consider them, sometimes it can cost a lot of money. It is not practical to do it. So it is also a matter of the health of the public, the safety of the public. For example, if you look at the example that I give just now in terms of the COVID, right? COVID-19. So if we take into account those hypersensitive people, then we will not be able to get this vaccine to the population that easily, because we will have to make sure that the vaccine is really work, and then it really takes into account those people, and then it will take like many years, 10 years, 20 years, and then at the point of time many people will suffer from the COVID. Yeah, so that's my take. Sometimes there will be some trade-off, and although it's not to say that they are not important, they are also human, right? We are all have to take care of each other, but then sometimes it is like that. To ensure that the public is really protected, we have to come up with a policy that take care of mostly on the average people first. Yeah.
I see. And as you mentioned, regarding to the determination of non-observed adverse effect, you mentioned it can be directly determined from the experimental data. So from the dose and response curve, can we just directly mention that NOAEL is similar to the threshold concentration?
Yeah, Noel, it is experiment data. Threshold is mostly on it is not really considered as really experiment data. Threshold is what we determine from the graph, from the dose response relationship. But then if we talk about Noel, it is the real experiment data that is determined. So the threshold can be a bit higher, but then the Noel must be from experimental data. Yeah, that's the difference between the threshold and the Noel, right? So that we have certainty, right? When we talk about toxic, right? Toxic substance that we are to the environment, to the population, we have to have that kind of certainty that this kind of those will not cause toxic effect to the threshold itself. Then there may not be experimental data. Then it could have large uncertainty then we will never know because we don't have any data. Yeah, that's the difference between these two.
So we couldn't say directly that Noel similar to threshold, yeah, because it could be
you cannot say that,
underestimate or even overestimate. All right. And regarding to the animal testing for conducting the toxicity test, you mentioned some example, but in general, is there any criteria for determining or for selecting the type of animals, yeah, for the certain assay for the toxicity? For example, you even gave us the example using, how to say, frog, yeah. In most cases, we use rat or something. Should we consider about the how to say, the sex of the animal or other considerations?
Yeah, it's very important to consider many things like the gender of the animals, the type of the animals. Then we have the age of the animals. Yeah, all this actually takes into account when we want to carry a toxicity study. And then if we want to get a dose response relationship, it is important to look into what kind of animal you're testing. And then it's also important because different animal, they'll give different response. And that's why we have these uncertainty factors, which integrates into whether we are using which kind of animals and so on. But then, yeah, that's uncertainty because human testing is almost impossible when we talk about toxic substance, which is why we have to use animals. And then, of course, to make sure that it is more effective when you're using animals, right? We sometimes use those like monkeys, right? Like yeah, those animals are closer to human. And then we also use like a per unit weight, right? So that we can actually, because there's a correlation between the weight and the toxic effect, so we can actually make sure that it is closely resemble human. Yeah, that's just the thing that you have to be aware of. But then of course different animal will also have different effect tolerance. So and also the certain part of the animals, right? Sometimes they are useful for certain type of drugs. For example, we are also using not only frogs, also some people are using rats, some people are using rabbits, some people are using I think many kinds of animals, and different animals, they have different parts of body that can be used for this kind of testing. Yeah. So yeah, but unfortunately, as I mentioned, we cannot use human. Yeah. If we can have human, then that would closely resemble what we want to get, right? The data, it would be more realistic.
Yeah, would be the great issue, yeah, if we directly use human for testing. All right, thank you, Dr. Wenda.
Yeah, but human usually is unintentional, as in yeah. Yeah.
Yeah, and must be the huge cost, yeah, if we use human directly for the testing. But anyway, maybe it would be very challenging, yeah, to extrapolate the data that we obtain from the animal testing to be applied for the human, yeah. For example, if any type, each type of the animal testing has different tolerance, so how to extrapolate that the dose that we just determined from the testing can be applicable for the human?
Usually for toxic substance, human is difficult to get. But then for drugs, we have quite a lot of data, because for drugs, they have to go through several stages. So they have to go through the animal stage first, then after that they'll go to the human stage. So for drugs, it is like things that is beneficial for us, and we'll have a lot of human data. So we'll have a lot of dose response relationship. Yeah.
I see. Any question from student or other participant, please? Yeah, you can deliver your question in Bahasa, no problem, if any. No question? Dr. Wenda, if possible, could you please also send us the PPT file of this presentation?
Oh yeah, I already put it in the chat. There's a link to
Yeah, very excellent. Yeah.
Yeah, usually I will put the slides earlier, but then this week because I was in the hospital, so I was unable to upload it. Yeah. So but I got to upload it yesterday, so you can get the files there. Yeah.
Thank you very much. It's excellent. Yeah, for our report. Still any question from the participant? No? Yeah. Since the time is up, so now 8:42. Again, Dr. Wenda, I deeply appreciate for your great effort, even though now you are still in the hospital. But yeah, you did excellent lectures, yeah, even though from the recording. Thank you very much, and this give us very insightful, how to say, understanding, especially how to elaborate the meaning of those response. Yeah, sometimes we just take it simply only to determining the LD50, but in this case, we even can elaborate many concepts. All right. So we can close. Yeah, don't worry, Dr. Wenda, so you can take your time and you may leave because the lectures is finished for today. Thank you very much as well to all participants and also the students who just attend these lectures, yeah. And we will meet you again next week for the third meeting of our environmental toxicology. We do really hope that Dr. Wenda can get fully recovered from the COVID, yeah, and also he also can recover very well from the cardiac issue. And yeah, I wish you also a great health and looking forward to see you again next week. Thank you very much for all of your great attentions. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Thank you, Dr. Wenda.
Oh, thank you. Just now my doctor came in to talk. Yeah, so sorry.
Yeah,
Thank you.
don't worry. The lecture just closed, and then yeah, you may leave. I'm really, how to say, hope that you can get recovered very soon. Yeah.
Thank you.
All right. See you next week. And yeah, wish you a great day. Okay, bye-bye. Ya, untuk mahasiswa lainnya mungkin dipersilakan leave, tapi mungkin saya akan close dulu untuk lecture ini karena akan digunakan record untuk pelaporan Wood Class Professor, Wood Class University Program. Jadi saya akan close dulu untuk link ini untuk mahasiswa yang akan mengambil perkuliahan analisis kimia lingkungan. Saya akan sediakan kembali linknya setelah saya close session ini ya. Terima kasih. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Terima kasih.